In section 8.4, we're going to be looking at annuities. Now, previously we have studied interest-bearing accounts where we have put money in as a lump sum and we calculate the amount of interest that we obtain over time on that lump sum. Here, we're going to be looking at an annuity. So what is an annuity? Well, an annuity is an interest-bearing account into which we make a series of payments of the same size. Now, this is usually a little more common than a lump sum account because people don't generally have, like, say $50,000 as a lump amount of money to put into an account. They do sometimes, but more common it would be that someone's going to make consistent payments into an account. And so again, that's called an annuity. So if we put the same amount of money into an account like each month, then that is an annuity. Now, an ordinary annuity is an annuity for which one payment is made at the end of every compounding period. So maybe at the end of each month or at the end of each quarter. The future value of an annuity is the amount in the account, including interest, after all payments are made. So maybe we're going to pay into an annuity for, say, 20 years. So at the end of the 20-year period, that would be the future value of the annuity. So we're going to calculate what the value would be in the future. So let's begin by looking at an example. Example 1. In January, you begin making monthly payments of $100 into an account that pays 6% interest compounded monthly. How much money will you have in the account at the beginning of July? So we're going to put $100 in the account in January. We're going to put $100 in the account in February, another $100 in March, another $100 in April, another $100 in May, and another $100 in June. So we're at the end of each month, we are putting a deposit into our annuity. So what we want to do is calculate how much money we're going to have in the account by the beginning of July. In other words, at the end of June. Well, this $100 that we put into the account at the end of June, we're not going to have gained any interest on that. So at the end of June, we will just have that $100 in the account. We will not have obtained any interest. But for May, we will have earned 1 month of interest. So this $100 that we put in at the end of May, by the end of June, we'll have earned 1 month's worth of interest. And April will have earned 2 months' worth of interest. This $100 from March will have earned 3 payments on interest. This $100 from February would have gotten 4 payments of interest, and January's $100 would have gotten 5 interest payments. So we're going to be able to calculate the value of this $100 at the beginning of July, or again, really the end of June. So when I put this $100 in at the end of June, what's the value? And so to do this, we're going to just use our compound interest formula. So our compound interest formula, if you'll remember, is that the future value, A, is going to equal the principal times 1 plus the interest rate divided by the number of compounding periods, and that's going to be raised to the n power, which is the number of times that we do the calculation. So for this money that we put in January, the value, the future value at the start of July is going to equal that $100 times 1 plus the interest rate, which is 6%, so 0.06, divided by M, which is the number of times we compound per year, so we're compounding monthly, so that's going to be 12, and that's going to be raised to the 5th power because at the beginning of July, we will have received interest payments 5 different times on that $100. So if we take 0.06 divided by 12, that's going to be 0.005. So what we really have here is 100 times 1 plus 0.005, so 1.005 raised to the 5th power. So if I bring in my calculator, 100 times 1.005 raised to the fifth power, that is about $102.53. So this $100 that we put in at the end of January, by the beginning of July, is worth $102.53. Now, in the same way, this $100 that we put in at the end of February is going to have a future value of 100 times 1 plus 0.06 divided by 12, but this $100 will only have interest compounded 4 times. So that is going to be 100 times 1.005 raised to the fourth power. And again, the 1.005 is coming from the fact that 0.06 divided by 12 will be 0.005, and 0.005 plus 1 is 1.005. So if I take 100 times 1.005 raised to the fourth power, that is $102.02. So this $100 that we put into our annuity at the end of February will be worth $102.02 at the start of July. Same idea for March. A is equal to the $100 that we put in at the end of March, and it's going to be times 1 plus 0.06 divided by 12. But for March, from March to the end of June or the beginning of July, we'll only have received 3 interest payments. So it will have received interest in April, May, and June. So that is 100 times 1.005 raised to the third power. So 100 times 1.005 raised to the third power, that is $101.51. So this $100 at the beginning of July will now be worth $101.51. How about April? Well, April we're only going to receive 2 interest payments, and that would be for May and June. So 100 times 1 plus 0.06 divided by 12 raised to the second power. So in other words, that's 100 times 1.005 squared. So 100 times 1.005 squared, that is $101 even. For May, we will only receive interest 1 time by the beginning of July. So that's going to be 100 times 1 plus 0.06 divided by 12 raised to the 1 power, which is just 100 times 1.005 raised to the 1 power. And so that is $100.50. So this $100 will receive 1 payment in interest at the end of June, and that would be 50 cents in interest, so now that $100 is worth $100.50. And finally, the money we put in at the end of June, it will not have received any interest, but if I continue my pattern, that would be 1 plus 0.06 divided by 12 raised to the 0 power, because there would have been no interest payments. So that would be 100 times 1.005 to the 0, and 1.005 to the 0 is just 1. So that $100, since it hasn't received any interest yet, is literally just worth the $100. So the total. What's the total value of this money that we've put in from the end of January to the end of June? So we've put in a total of $600. What's it actually worth? Well, $102.53 plus $102.02 plus $101.51 plus $101 plus $100.50 $607.50 plus $100. So I'm just adding up these values here. That is equal to $607.56. So this is $607.56 when I add this up. So this is how an annuity works. So for this money that we put in at the beginning, we're going to get interest, each month. And then this, we're going to get interest each month after that, and so on. But if this is getting interest for 5 months, then this is going to get interest for 4 months and 3 months and so on. Well, we could generalize this and do this same kind of thing for years. So if we put in this $100 not just for 6 months, but say if we did that for 10 years, then the first $100 would get interest for the entire 10-year period. Now 10 years, that would be 120 months. So we would have this interest for 120 months. So this number here would be 120 months. And then this would be 119 months and 118 months and so on. So we could do that whole thing to figure out what the value would be at the end of 10 years. But that would be a whole lot of calculations to go through, and that would not be very fun. So we don't really want to do that. So we want to come up with a formula that we can use for that purpose. And so that's what we have right here. We have a formula for finding the future value of an ordinary annuity. Now, the mathematics that we could use to come up with this, I will show in a separate video. But for now, I just want to accept this and demonstrate how to use this formula. And then a separate video, I'll show you where this formula is actually coming from. So a formula for finding the future value of an ordinary annuity. Assume that we are making N regular payments R into an ordinary annuity. The interest is being compounded M times per year, and deposits are made at the end of each compounding period. The future value or amount A of this annuity at the end of the N periods is given by the formula A equals R times this big mess. And so in these parentheses in the numerator, I have 1 plus R divided by M raised to the N power. That's like what we did here in the parentheses, minus 1, and then that's all over R divided by M, close the parentheses. Now again, in this formula, A is the future value, so that's what the value is going to be after the end of all the time period. R is the amount of our regular payments, so like in this example here, that's like the $100. The lowercase r is the interest rate written in decimal form. M is the number of times we're compounding per year, so that's like the 12 here because we're compounding monthly. So that would either be like 12 for monthly, 4 times for quarterly, once for annually, and so on, like it's been in the other kinds of examples that we've been looking at. So we're just taking R divided by M, and then N is the number of times that we actually do the calculations. So again, like if we're compounding monthly and we're doing that for 10 years, then there would be 120 different times that we do the calculations. So that is the number of periods that we do the calculations. So to close this video, I want to repeat example 1 that we just did up here. But instead of calculating it individually and adding it all up, I want to use this particular formula. So if I do that, for this problem, we're wanting to find the future value, the future amount. And our regular payments were $100. So R is equal to $100. Our interest rate is 6%, R 0.06. We're compounding monthly, so M is equal to 12. And we're doing that for 6 months, so that is 1/2 of a year. And so that means N is going to equal 12 times 1/2, which is 6. And that's all we need. I can fill in my formula based on these numbers. So the future value after the 6-month time period, so at the beginning of July, is going to be the $100 times, parentheses, 1 plus 0.06 divided by 12, that gets raised to the 6th power, minus 1, and that's over 0.06 divided by 12. Now I could type that in my calculator like this, but it would be better to clean it up just a little bit. So as I did when we were looking at example 1, 0.06 divided by 12 is 0.005, and 1 plus 0.005 is 1.005. So I have 100 times this is 1.005 raised to the 6th power minus 1, and then 0.06 divided by 12 is 0.005. Now this is much nicer to enter into my calculator. And so I'm going to enter that. I'm going to write down how I'm going to enter that. I'm going to enter that as the $100. I should put dollar signs here. That is dollars. And I'm going to put times 1.005 raised to the 6th power minus 1. So I'm going to put the numerator of this fraction in parentheses, and then I'm going to divide by 0.005. So as long as I simplify here, then I can enter it in like this, which isn't bad for entering. So if I bring in my calculator, 100 times parentheses 1.005 raised to the 6th power minus 1 close parentheses, and then that gets divided by 0.005. And so that gives me $607.55. So after the 6 months, at the beginning of July, these payments will be worth $607.55. So again, what I've done is I've put in 6 different payments of $100. So I've put $600 into the account, and at the end of the 6 months, it's worth $607.55. Now looking back up here, we got a total of $607.56. So we've got a 1 cent discrepancy. The reason why we have that 1 cent discrepancy is because I rounded each one of these to the nearest penny. Had I left this out to fractions of pennies, then this would have also come up to be $607.55. There wouldn't be that discrepancy except for the rounding. So there's our first couple of examples of dealing with annuities. We're going to pick up with the next example in a new video.